Hi, this is John Bleiler, Editor-in-Chief of Chip Design and Embedded Intel magazines. I'm here today with Alan Coppola, who is the president and founder of OptNgn Software, and he's going to talk about their latest release of FFT algorithms for both the ASIC and the embedded space.
Just this week we released our second library of fast Fourier transform components and for FPGAs, but also we can convert those to ASIC for anyone who's interested in that. And basically we're taking a little bit different tact both in our delivery method and our sales method. But before I talk about that, let me just mention exactly what they are. They're fixed point FFT components. It's a full-up library. There's 264 elements in the library. And they're all parameterized by fixed point size, by point size, complex point size, and whether or not the output is scrambled or unscrambled. So some things like that that the user can choose from. And the processing speed on a typical modern FPGA is around 250 million complex samples per second, which is enough to do quite a few of the various kinds of spectral applications that the users want.
Does that transfer to a certain throughput?
Yeah, that's the throughput. It would be 250 million complex samples a second, which translates into a certain number of being able to, like if you're doing image processing, that translates into a certain number of being able to process a certain number of megapixels per second.
Okay.
And if you're doing any kind of spectral analysis, it translates into how much throughput you can get. Yeah. So we have the library, and it's available right now, and you can immediately download the elements, and you can pay for them using PayPal.
Good. Convenient.
And so we've broken them all out into individual elements that you can purchase. Each element comes with the usual thing, which is basically a Netlist for multiple vendors. The vendors we cover are Xilinx, Altera, and also we cover the Mentor graphics precision synthesis tool, which allows people to take the Netlist into Mentor graphics precision synthesis and then map it to any of the vendors that they cover, which includes Xilinx and Altera and Lattice and Actel and any others that the tool covers.
So that's nice coverage of both the ASIC and the embedded space.
Yeah, it would allow you to convert your design to an ASIC design, but probably you would want to buy our RTL library to do an ASIC design. The Netlists we're selling for instant download are FPGA Netlists. Okay. So if you wanted to then convert that to an ASIC design, we would sell you the RTL Netlists that are optimized for the ASIC design.
Okay. And you had an interesting business model with this too. It's kind of an iTunes almost, right?
Yeah, exactly. We've taken the library, and we're selling individual elements. So you click on an element, and you pay anywhere from for Xilinx or Altera, you'll pay anywhere from $60 to $300 for that one element, and you'll download it and you'll unpack it. You know, when you get the password and stuff, and you unpack it, and there you are with your model ready to go with the synthesis wrappers and simulation and the simulation test bench. So the entry price for any one element is pretty inexpensive.
Seems reasonable.
Yeah, and and that way the user can get exactly the element they want. Like iTunes, you get the song you want, but if you want the whole album, of course, it costs more.
More, that's right.
So yeah, it is kind of like an iTunes model, and so that's the sales model is definitely to take our elements and sell them individually, take each element and sell it individually. Right now we have certain fixed point widths, and then the libraries will cover in the future, because this is sort of like the beginning of a chain of libraries that we'll be releasing. And so the libraries we'll be covering in the future are the two-dimensional fast Fourier transforms, and then we'll have real Fourier transforms. And
The 2D, what would be the applications for
well,
those?
imaging.
Imaging? Okay.
Yeah, I mean, mostly imaging. There's a specific kind of imaging stuff that you do called convolution, called convolution coprocessing, where you take a two-dimensional image. It could be any kind of video or stream or anything like that, and you'll fast Fourier transform to get it into the frequency domain, and you'll apply various kinds of filters and then you'll inverse fast Fourier transform it, and you'll end up with peaks. So the filters could be objects that you're looking for, like perhaps you're looking for faces, and so it's used in things like various kinds of object recognition, be it faces or whatever you're looking for, really. And then you would, so that's one particular application domain. So the two-dimensional library actually is using pretty much the same technology as the one-dimensional library, but as with most of these things, you have to walk before you can run.
Very good.
And we also have a link in with a partner, Impulse Accelerated Technologies. We have a link in with their C to FPGA tool, where we supply an interface to our FFTs that allow you to then use their C to FPGA compiler, and then call our elements, our external elements.
For higher level modeling, I guess?
Yeah, basically
just
users who want to use C as their input language instead of Verilog or VHDL, sometimes you need these external IPs that are kind of units or chunks, and you want to be able to program in C, but then you say, okay, I want to call this coprocessor over here, and I want to do this convolution coprocessor, because that's a way to accelerate even what you're doing inside you're still working inside the FPGA, you still get transformed to an HDL, but the bottom line is not everyone wants to do these kinds of IP. They're just take too much time to do. So you would do so you would definitely do your C program, which, oh, by the way, you then can use as a software model, and then you can synthesize it, and then you can call this external IP, and if you're using it as a software model, you can call a software model of the IP. So you can kind of put this all together into a system where at the end of the day, you're blowing it through a bit stream into an FPGA, and you're getting this acceleration.